A weather map. Red over Texas, blue over Minnesota. Hot next to hot, cold next to cold. This isn't random, it's spatial autocorrelation. Nearby locations have similar temperatures because they share the same climate system. In tissue biology, spatial transcriptomics measures gene expression with location. A gene expressed in one spot is likely expressed in neighboring spots. The same spatial structure that makes weather maps interpretable makes tissue maps interpretable. Spatial statistics is how you read the map. Tobler's first law of geography: everything is related to everything else, but near things are more related than distant things. This is the foundation of all spatial statistics. In a tumor section, immune cells near the tumor margin behave differently from immune cells deep in the stroma. Gene expression changes gradually across tissue layers, not in random patches. Spatial structure is the norm. Randomness is the exception, and detecting that structure requires methods that understand proximity. Before computing any spatial statistic, you need a spatial weights matrix, who is each location's neighbor. For a grid contiguity, locations that share a border. For irregular points, distance-based, all locations within a radius. Or k nearest neighbors, the k closest locations regardless of distance. In spatial transcriptomics, neighbors are typically defined by physical distance between spots or by Delaunay triangulation. The weights matrix W has entry Wij equal to 1 if locations I and j are neighbors, 0 otherwise. Rows standardize so each row sums to 1. Moran's I measures global spatial autocorrelation. It compares each location's deviation from the mean with its neighbors' deviations. The formula, n divided by the sum of weights, times the sum over all pairs of the product of deviations weighted by the spatial weights, divided by the total variance. I near +1 means strong positive spatial autocorrelation, clustered. Hot next to hot. I near 0 means no spatial pattern, random. I near -1 means negative autocorrelation, a checkerboard pattern. Significance is assessed by permutation. Shuffle the values across locations 10,000 times and compare observed I to the null distribution. The Moran scatter plot puts each location's value on the x-axis and its spatially lag value, the weighted average of its neighbors, on the y-axis. 4 quadrants emerge. Upper right, high value surrounded by high neighbors, a hotspot duster. Lower left, low value surrounded by low neighbors, a cold spot cluster. Lower right, high value surrounded by low neighbors, a high outlier. Upper left, low value surrounded by high neighbors, a low outlier. The slope of the regression line through the scatter plot is Moran's I. In spatial transcriptomics, compute Moran's I for every gene. Most genes have low I, their expression doesn't depend on location. But some genes have high I, their expression is spatially patterned. These spatially variable genes mark tissue domains, gradients, and boundaries. This is step 5 of your spatial pipeline. Moran's I identifies the genes whose expression carries spatial information, filtering thousands down to the most informative for downstream analysis. Tobler's law. Spatial weights define neighbors. Moran's I measures global autocorrelation. The Moran scatter plot classifies every location. Permutation tests assess significance. Next, finding exactly where the hot spots are.